All right, so that's the title of this. So if you're in the wrong room, if you're looking for something more exciting. The session that we're in, we're going to be talking about how some of the things coming into Java actually were a pretty big decision maker for us. So we had done some prototyping in Java, and we know Java. The developers in our group know Java and love using it, but we weren't going to be able to use it for our production product that we were building. So it was kind of off the list of things we were considering. I wanted to talk about some of the reasons why it didn't just get back on the list, it actually went right to the top. So this is going to be pretty fun. Now, this is the first time I've ever done this presentation, so if you've never spoken publicly, I'll tell you, one of the hard problems about speaking is that you never know how much each slide is going to take. So sometimes I'll talk on one slide for 10 minutes, sometimes it's 5 seconds. So sometimes, I get to the end of my presentation and only 6 minutes are gone, and sometimes I'm still on slide 3. So hopefully I'll have planned this out well. So I started with Java in 96, 1.0. I downloaded it. First thing I wrote was a disassembler and decompiler because I wanted to see all the code that they didn't ship. It wasn't open source at the time. They had some of the source code in there, and I took the first half an hour after I downloaded it. I was like, I'm never writing C++ again. It was just everything I liked about C++ was in Java, and all the things I hated in C++, most of them were not in Java. So, I started a company with some friends 25 years ago, Tangasol. Built a product called Coherence. It was the first clustered in-memory data management system. So you've probably heard of dozens of them now. I mean, it's pretty popular for scale-out architectures. And Oracle bought us in 2007, and I left in 2015 and doing a new startup focused on cloud. And we also have a foundation for some of the technology that we're doing, which is the Xqizit Foundation. And then the last bullet I just threw in there because someone asked me the other day, well, I thought you retired. It's like, retired? No way. I'm having way too much fun building stuff. I can't even imagine. Actually, my co-founder is a pretty wealthy guy who, from tech startups and stuff. And he's dramatically older than I am, and He's like, if you would have told me how much fun this was, I would have joined you on day one. I wish I knew. So why this topic? Well, first things first. Being in a startup, everything you do is selling, right? I've been startup after startup, and everything I do is, and it's not like I'm trying to sell you something right now, right? Today, it's more that, if you believe in something and you want people to look at it and use it, you have to be selling. But, I'm not selling today. What I want this to be as a presentation is like a celebration of the work. And I see some of the faces in the room that have been working on this for years. This is a celebration of stuff that actually made a significant difference to us in terms of what our plans were and what we were able to achieve. So, secondly, I want to put this within the context of what we're trying to do. And it's not a typical thing that we're trying to do. So it's not like you can just take everything I'm talking about and be like, yeah, I'm going to go to work and plug that in. But we had two significant goals that we had to achieve. And they actually they're not two separate goals. They're tied together twins that are born conjoined, right? These things go together very, very tightly. And that's security and density. We literally want to put about 10,000 applications on a single server. 10,000. That's our goal. And to do that, we have to eliminate every possibility of security issues, because if you're putting multiple apps on the same machine, they can't even know that there are other apps on the same machine. There has to be no way for them to feel them, touch them, screw with them. Those things have to be just impossible. It's not that those things have to be hard. They can't, the possibility can't exist. And I want to talk a little bit at the end about some of the things that hopefully I'll inspire someone in the Java community to say, hey, we could do that. We could use that. We could put that in the JDK. So some disclaimers. Like I said, these are some unusual requirements that we have. So don't try, oh wait, no. Do try this at home. Like, definitely, like, do try it at home. But just remember, don't expect what I'm talking about here to necessarily map to what you're doing. So, I hope you enjoy this. I hope you learn a lot from it. I hope it inspires you to things you might be able to use Java for. So the work we're doing is on a project called the Xvm. It's still in the R&D phase. So I want you to understand that even though I'm pretty confident that I'm always right, it often turns out that that's not true. So don't mistake my confidence for my correctness, okay? With that out of the way. So like I said, we wanted to build an ultra-dense, what we call an autonomic cloud platform. And what this means is, I ask people a question like, anyone here ever shop online, buy something at Amazon? 1, 2 people, 3, oh, still awake, okay. And it's like, how many times, so here in the States, I know a lot of you have traveled here from elsewhere, but Amazon here in the States is pretty prevalent. And I've never talked to anyone on the retail side of Amazon, never. I've talked on the technical side and stuff like that, but, in terms of software development and stuff, but I've never talked to anyone on the retail side. And I've bought a few things from Amazon over the years. Probably this came from Amazon, so probably most of my clothes came from, I don't know, like, I have a few things from Amazon, but I've never had to talk to someone there. And that's because their systems are designed for self-service, right? Like every time you have to talk to someone at a company like that, they should be looking at that as like, how could we have prevented needing to talk to them? And my goal with software is not that I don't want to talk to users of the software. I love talking to people who use software that I work on. It just makes me happy to, even if they're complaining about it, I want to hear it, right? And but the thing is, they shouldn't, if you're building software, the people who use it shouldn't have to talk to you, right? If they have to ask you questions, if they have to complain, whatever it is, it probably means you could have done something in the software that would have prevented that. So that's the autonomic side. So we want these applications as they're deployed, we want them to somehow just appear in the web, on the internet, ready to go. And you shouldn't have to think about, like, do I have to call someone? Do I have to provision something? All those things should just be as automatic and autonomic as possible. But we needed a runtime to do this. And we looked at a bunch of runtimes. The only one that comes close to the requirements that we have, and in fact, Cloudflare is using it for this purpose, is the JavaScript runtime. So it's kind of interesting because JavaScript was designed to run in a browser without adding to the billions of security issues in Windows. They wanted, without adding to those, security issues, they wanted JavaScript to run in the browser and not allow some website to take over your machine, right? So you can imagine we're kind of going for something similar. We need a sandbox, is what we call it in Java, right? We need something where we can put it on the server, put your app in there, and your app can't even tell that it's on a server. So the problem is, though, if you change the fundamental construct of the runtime, the languages that we build with today are all built around a concept called layer cake, right? So we have hardware, and we have firmware, and we have operating system, we have libraries that just happen to be on your file system. And then you have, the JVM perhaps, and you have libraries for the JVM, and one of them you didn't actually put there, it just came with something else that Gradle grabbed from Maven, grabbed from, I don't know, like, and then at some point there's a issue in JNDI, and it goes and grabs that library that you never even used, and now they took over your server, right? So that's called a layer cake architecture, and that's how you give a hacker control of your data center, right? So we didn't want to do that for obvious reasons. So, like I said, we did evaluate a bunch of options. We looked at Go, we looked at Java. JavaScript's the closest, but I would never be able to forgive myself. So we prototyped all this in Java, built a prototype compiler, and because Java didn't have the capabilities we need, we just used it for prototyping. We built an interpreter, which is about as fast as a turtle. But it's not supposed to be fast. It's a proof of concept. Like, can we do this? Can we not? Like, what are the benefits for this? How does this feel to use? And then our goal was to build a production backend using LLVM as a emitter of a code that we could then load through say crane lift. So we're looking at WASM. Anyone know what WASM is? Yeah. So for those of you that don't know, WASM is like 8086 but in a web browser. Pretty much exactly, except some endianness confusion and things like that. But so it's a way of expressing code, kind of like Java bytecode, except dramatically lower level. So literally, it's like memory. Yeah, you have to allocate it, and you've got 64K to work with, and things like that. So it's kind of old school, but in a browser. Old school in a browser, like if you took an Apple II emulator and put it in JavaScript. The thing is, though. And there have been a couple talks this week about this. Like, community matters, and the way things are organized matters. And the problem in JavaScript is you have two communities, and they hate each other. You have the everything should work in the web browser community, and you have the we're going to steal JavaScript and use it on the server side. This is the WASI debate. And they were building fiber support and things like that we needed. And then they decided they hated each other, so they hated each other so much that they were going to kill the whole thing. So at some point, we're like, this isn't working out exactly the way we thought it would. Sorry. So we ended up needing to kind of go to Plan B and Plan C on our list for like what we were targeting for a back end. So I'm going to start with something really simple. Like, this should be insultingly simple, right? What does foobar stand for? Does anybody know? Don't say it out loud, please. Just look it up on the internet and not at work. So this is where you've seen all these examples, like foo calls bar. Well, that comes from this foobar. And so I'm just following the rules here. We have foo calling bar, right? And, oops, that was the wrong button. So say we call it from some run method, right? Nothing surprising here. So run calls foo, goes to bar, and bar, by the rules, like I said, I'm not making this up, bar has to call baz. I don't even know where baz came from. So, and then we return back to bar, and we return back to foo, and we return back to run. So if this is all you learned today, I'm sorry, because that's not very, very good. But we often take that picture, and we'll draw it as a stack, and we call this an execution stack. This is actually how it sits, I say on the CPU, but this is how it sits in memory, right? So if you, and by the way, sometimes this gets drawn upside down because computer scientists never know. When they say tree, they often put the root at the top. And when they say stack, they often put it upside down. Maybe they're Australian, I'm not sure. You've probably heard of SP, like, or ESP or whatever. Basically, it's a stack pointer. It says, and if you look at assembly, it's like, what is it doing SP minus, right? And it's because the stack grows up. So it's like your variable, your local variable, when you say for int I equals 0 to whatever, it's somewhere in that stack frame, and the top of the stack is here. So you have to go down to get to your I, right? A little bit lower level than most people need to know in Java, but that if you ever look at the assembly code that hotspot's emitting under the covers, that's what you'll see. So these are stack frames, and a return pops the frame, and a throw, we say it unwinds. Could be a long jump. That was the typical implementation for many years. But basically what it has to do is, because they're intermediate frames that have no care about the exception, you've basically got to somehow pop multiple frames off, and that's a C runtime library function called long jump, which does that for you by unwinding the stack. The problem, though, and this is a fundamental problem that we had to face in our design, is that if you're in Baz, everything under you is stuck. Like, yeah, you can throw to get back there, but that's like a pretty heavyweight way to like, and it's even worse when you're trying to do multiple things. So go back years to when we only had like single core computers, like single threaded operating systems. I mean, Windows didn't have threads. It had, one CPU just doing one thing at a time, no threading. And so if you had one window, and you put another window up over it, the window under it, like the code was like stuck on the stack. It was suspended, both graphically, but also at the processor level. The code that called the window to go on top of it, that code actually sat on the stack on top of the code. So when you open the new window, that code sits on the stack of the window that's already open, right? And so if you want to get back to that code, like, because it's not multi-thread, it's stuck. You can't get back there. And so this is a fundamental problem that was solved through a concept called fibers, and we'll get to that in a second, though. So when we talk about threads, I've got to like split this into a couple different words here, right? Because we have this concept of a logical thread of execution. Like, and this is what, think about it as a whiteboard thread, right? Like you go to a whiteboard with markers and you're explaining this is going to do this and then it's going to do this. It's the logical thread of execution. It's how you think as a developer about your code running, right? So when we looked at the foobar example, that's a logical thread of execution. Physical threads, sometimes they're called hardware threads, physical threads, etc. They're not actually threads. What it really means is a CPU, but a CPU that only runs one thread. So like a CPU today, you can't really buy one that only runs one thread. And that's because inside the CPU, inside the CPU package, it basically has multiple CPUs. So we talk about cores, we talk about SMT. Where this came from initially, obviously like Sun, for example, was doing multi-processor workstations and servers, but Intel was looking at like, how do I make this one thread CPU really, really fast? They're like, well, we could just keep adding units to the CPU so that we could look ahead in the instruction stream and grab an instruction and execute it at the same time as another instruction. So they ended up with, if you will, a core that had way too many execution units that weren't getting used. So some other engineers said, well, what if we actually ran another thread on the spare execution units that weren't getting used? And that was called hyper-threading, or what it's called generically as SMT. So basically, however many things can be going at the same time on the CPU is what we call physical threads. OS threads basically just are a representation, what we say at the kernel level, of your code being mapped to, being told to run, if you will, on one of those physical threads. And then virtual threads, and this is what's fairly new in Java. Virtual threads allow, instead of that being done at the OS level, it puts another layer on top in the user level, so user versus kernel. At the user level, you can schedule your logical thread of execution, if you will, your code, onto an OS thread, which then the operating system puts onto a physical thread, and that's how the code gets run. So why is this important? Well, we needed to support something called fibers. Sorry for my pictures, but the idea is, you're taking a thread and chopping it up, right? So a fiber is basically some small unit of time, some small unit of work, task perhaps, something like that you can place onto a thread, right? So it's completely different from a thread, right? It's a fiber, it's not a thread. And the way we know is that it has an entry point, which is kind of like a thread. And it also terminates, when it returns or you throw an exception and it doesn't get caught, right? Which is actually, that's kind of like a thread too. So it's kind of like a thread, but it's different, right? So I'm going to do a slight detour now. We're going to talk about something we call services. So this should be, if the sentence is up on the screen that I'm thinking, yes, this is the most dense sentence I have in the presentation. What a service is it's a von Neumann machine. It's an 8086 basically, right? It's got a CPU, it's got memory, and it runs one thing at a time in a serial fashion, and that's it. Like, it's a very simple piece of hardware, except it's not hardware, it's software. And we can connect multiple of these, like you could connect servers on a network, for example, and they can talk to each other. And as they talk to each other like with messages. They say, hey, run foo for me, run bar for me. And that thing that they're talking to, they send it a message. It gets delivered by a passenger pigeon, and they open the letter and it says run foo. It's like, okay, I'll run foo. And they run foo on a fiber. And the service, being an 8086, only executes one fiber at a time, at most one fiber. The reason this architecture exists is because computers are actually really good as long as they're not stepping on themselves. They're really fast. And the problem is when you have a shared everything model, a shared mutable everything model, you end up with basically hammering the memory bus on a server. So as we move to 500 and 1,000 core chips, already even at 64 cores, like the limiting factor is not the CPU, it's the memory bus that connects it to the memory. And our memory bandwidth has been doubling every generation, and it's still nowhere near enough. So Java, for example, completely saturates the memory bus on almost every high-scale benchmark I've ever seen. And it's because everything in the memory model everything is mutable, everything is shared global. So not at your code level, but below that where it's executing. And so so what that means is it's constantly having to go back and forth to memory and also across different cores to make sure that they're not killing each other and corrupting data. So we simplified that model and said within a service, that's the only thing that can read and write data within that service. So they communicate via messages. So I'm going to just look at a quick snippet of code here. So this is should look a lot like Java. This is the language designed for our cloud runtime. And so when I talk about cloud, I mean it's a lot of buzzwords. But what I mean is that like this code right here, this one file, you could compile it, stick it in the cloud, and it would just run, right? So everything is included in that module. So here we see the foobar example. We've got run. We're going to just time it for the fun of it. It calls foo, and foo is going to call into a service, a separate service called bar, and it's going to call it 3 times, right? And what bar is going to do is it's going to say, hey, I've got a future result. I'm going to return that result before I do it. And by the way, call me back in a second and I'll finish whatever. So this is a fake, like I'm doing something that takes a second. I just had to fake it for the example. So we can actually see this run. Let's see. So we'll build and run this. And it's terribly fast. Because it takes 3 seconds, right? It's got 3 1-second operations in a row. So the reason I wanted to show this is, your typical application development, you don't want to be thinking about, atomics and queues and you just do this. You want to be able to write application logic in a simple, single-threaded manner. And you want it to scale in production to handle, thousands of users, but you don't want to have to be thinking about thousands of users when you're doing each operation within the application. Each service, being its own little computer, is asynchronous from each other service. So if I need to do asynchronous logic, I just need 2 services, and I have asynchronous, between the 2 services. And we've designed this to be able to support, literally millions of concurrent services. So here, what we want to do is asynchronously call multiple times to have that work done. Here, we'll go jump in. I've got an async example. So all we have to do to get this to work is to take a future when we call the bar. And what that says is, hey, go over there, but I actually know that it might be asynchronous. So just go ahead and tell it to do it, and you'll give me the result back, in my future Boolean. So it's not a Boolean, it's a future Boolean. And then here you can see all I'm doing here is waiting for the 3 of them by anding the results together. Take the 2 results and stick them together. Take the 2 results, stick them together. Get the result, which waits on the 3. So what would you expect in terms of how long this would take? It's all async, but it's all to the same service, so it should still take 3 seconds, right? except the service isn't actually doing any work. It sets a timer, and then when it sets the timer, there's literally nothing running. Like there's no call stack. It's gone. It's a reactive style of development. And the reason we did this is because we want to take an application, and the second that it's not doing anything, it's not there. It's literally gone. We take it out of memory, we stick it on disk. Like the next request comes in, we're like, oh no, it's here, ready to go. And this is the only way, especially with the main limiting factor with multi-tenanted hosting is memory. It's not CPU, it's not storage, it's not network. You run out of memory long before you run out of anything else. So here you see it was a second. And that's only because the timer is not actually working. If I made it do actual 4 loops of counting apples or something, it would actually take 3 seconds. And so the thing I want to get across here, though, is that we still have the logical thread of execution. But when we look at this picture, it's not a thread, it's a tree, right? So if we look from the top, we see, oh, run calls foo, and then it kind of splits and calls out. But when we look from the bottom, if we're in bar and we look up, we're like, oh, it's bar called from foo, called from run, and if we turn it around, we know run called foo called bar. So we just see the logical thread of execution. So anywhere you are in your code, like if you threw a stack trace, you wouldn't just want to see bar, you want to see bar and foo and run. And every single fiber needs that capability to be able to see where am I in my logical thread. So, the reason I had that scissors picture with the threads is it's a subsection of a logical thread. That is what a fiber is. It's a subsection of a logical thread that's bounded by the service it's executing within. So while it's in a service, while that fiber is in a service, it has full read-write access to everything in that service, right? And it knows that it's the only thing at that moment running in that service. We map each fiber to a Java virtual thread. Pretty obvious why we needed virtual threads now. So we do not preemptively schedule these fibers, just like Java doesn't preemptively schedule virtual threads. Like if you have a virtual thread that just does a loop of counting, that thread, once you start running it, it's not going to stop until it finishes whatever processing it's doing. Now, if it hits an I/O thing or something like that, yes, Java will swap it out, and that's why virtual threads are pretty cool. In our case, we use a concept called coloring. At least we describe it by coloring. So red and green. If you're curious on this topic, look up, there's a blog written called What Colors Your Function by a guy who does some language and compiler work out there. It is a controversial blog years ago, but the main thing is that as a developer, if you want your code to be interleaved as it's running, if it hits an I/O point and you want it to be taken off that service so other things can run on that service, you have to basically say this service is concurrent or this method is concurrent. What you're basically saying is, I don't mind if this code is taken off, but you don't know who called you. So anyone who called you, if they're not concurrent, you're not concurrent. Because we're literally lifting that fiber off the service, putting another fiber on. And unless everyone in that logical thread agrees, yes, I'm okay with that, then no one's okay with it. So everyone has to buy in, and this is how we protect, from memory corruption. And I'm not talking physical memory corruption. I'm talking your application data. So, virtual threads to the rescue. We had no way to build this on the JVM using, JVM bytecode or et cetera, until virtual threads existed. And the reason is, first of all, OS threads are obviously too heavyweight, and we're going to have millions and millions of fibers. At any given time, we may have millions of fibers. We would have needed thousands, maybe millions of OS threads. And remember that whole problem with the frames stuck? There are a bunch of optimizations you can do with this style of architecture that you basically charge ahead, right? So instead of like creating a message and putting it in an envelope and giving it to a bird and mailing it to Alaska and having them open the package and read the letter and figure out what to do so that it can add 1 and 1 and write a message back to you with the answer to and put it on paper and put it in an envelope and give it to a bird and send it back, and then you can get it, then you open it and then you read it. You realize, like, in a modern CPU, a typical modern CPU can do about 10 add operations in a single clock cycle on a single thread, right? And we just talked about, like, I don't know, 1 billion clock cycles to do, I don't know, a large number. 100,000, 100, it doesn't matter. It's magnitudes slower to do messaging. So what you want to do is, instead of doing all that I just described, you want to just call a function and have it return. The problem is, you're going from one service to another. You're going from one domain of mutability to another. And as you do that, you're crossing a boundary from a management perspective, from a management meaning I need to be able to kill an application on the fly or pause it or persist it or something like that. So it's almost like going from, you know, across different processes in an operating system, right? So as I go across that boundary, right, I still have a foot in the old one, like, because I'm on the execution stack, right? I still have all that stuff stuck under me now as I'm calling new functions. So those optimizations are key, but they're also extremely difficult in the world of operating system threads, because operating system threads are not manageable. Like, we don't schedule them, the operating system does. And, you know, so the stuff that's stuck under there, it's stuck until we return or throw back up to it. So Java virtual threads, huge game changer for us. Scoped value. Anyone use this yet? All right. Cool. A couple people. So going to take that same picture, run calls, foo calls bar, and when we're looking from the top down, we see this tree, and we want to infect that tree. We want to paint that tree, if you will. So scoped value lets us bind at a higher point in the tree and then obtain anywhere below that in the tree. So we fork, fork join, whatever. Like, any way we get down that tree, whether it's a call or a fork, we don't have to be passing the information in a parameter. We've literally infected the logical thread of execution with the information that we have to pass down. For example, I'm on the web, I have a request come in. Should I pass the request to everyone? And here's the problem with composing software, right? You have components that know about requests. That's all they do. They're built for the web. And then you have components, okay, so if I look at Java-lang string, it knows nothing about HTTP request. I look at streams. They know nothing about HTTP request, right? But I get to pass a lambda into it, and somewhere downstream, or I get to pass a method handle for a helper function, and somewhere downstream it's going to call some of my code back that does know about the web. And it's like, where's my request? Everything in the middle knows nothing about the request, so it can't get passed all the way through. It pops up over here on my code, and I'm like, hey, scoped value, there's my request. It literally pulls it out of the ether. So sessions. Who's the user? We're here at Oracle. Oracle has, across all their products, something called ECID. That was one of the one of the inspirations years ago for a similar feature. So records. So this is another new thing in Java. So why would this be interesting? A lot of languages have things called tuples. And this is basically like, hey, here's a couple things I want to just put it together, go. In Java, that would be 600 lines of code, because you have to toString and hash code, I don't know. Records, they're done. There you go, one line of code, we're good. Multiple return values. How many things can you return from a Java function? 0 or 1, that's it. What if you need to return 2? Used to be, you make a class, or you return an array of object and stuff stuff into it. These things were not beautiful. So we use tuples and things like reflection, parameter lists. So any function that takes 3 parameters, I can take a tuple that has at least 3 things in it of the right types and pass it in. anything that returns 5 values, I can take it back as 5 values, or I can say, give me a tuple back, right? So basically, our call sites, meaning the place where we call something, they are a nexus between a sequence of multiple things or a tuple. So both on the parameter side and on the return side. So records are a perfect fit for this. And immutability is also extremely useful for a lot of things. And it's mainly because it allows you to ignore potential problems. Immutability just says, I don't have to worry about that. And it frees up part of your brain. You like string in Java, right? Like, that's basically what we're talking about. And a nice other bonus that showed up in the JDK is the class file API. So we're planning on doing both ahead of time and JIT compilation. So hopefully we'll be leveraging the new class file API to do that. It's not an essential because there's so many libraries out there already that do assembly, but it's nice to have it built in. So I'm very, very pleased to see this, and I think it'll be pretty useful. We also have some other things that are not typical requirements. You know, we have to make sure that there's safe points in our code. And of course, the JVM underneath is putting its own safe points in as well. This is basically every so often, you never see it, but under the hood, it's like, oh shoot, I'm in a loop. I need to make sure it's not an infinite loop, and you know, because I have to stop if someone's doing a GC or interrupt, whatever. And it's like, so the generated code that the JVM spits out, every so many clock cycles, it's targeting a way of like, just, you know, sorry, just checking to make sure it doesn't have any messages, right? Oh, speaking of which, I do want to get a picture. I've never done this, but I've seen speakers do this, and I wish I remembered all the times I have spoken. So I'm going to say hi. But nobody left and ran to another room. We're obviously not virtually threaded. Sorry, I missed one point here I wanted to make. There is one thing that we need. The new operation in Java is the Hi John, I see you laughing. This is the one thing that is still a weakness for us. And we have a solution designed, but so the thing is, anyone here ever deploy in the cloud anything with Java? Yeah. So, you know, what do? You start out, you're like, give me an 8 gig VM. This should be plenty, right? And typically your app's using 3.5 gig maybe or something. And then one day it like uses 8 gig plus 1 byte and it dies. Like it's gone. Like your service is down, the internet's dead. So what do? You're like, oh, give me a 16 gig VM, right? And if you run out of memory over there, you give me a 32 gig VM, right? And most of the money that companies pay for the cloud is actually paying for RAM upgrades. So we want every allocation to be tracked. And that also means we need every deallocation to be tracked. We need to know when GC takes something back. So we have what's called a container model. And what that means is that all code in Xqizit runs on a fiber. If you're running on a fiber. And if your code in Xqizit and you're running in a service, because fibers only run in services. And services only run in a container. So if you're running code, you know you're on a fiber, you know that fiber is in a service, and you know that service is in a container. And if I'm in a container, I just create a container. Like you can create an array list. Well, you can create a container. You can put code in it and say, container, run that code. And the great thing about that is, if you're in a container, it's like your own universe. Where's the edge of our universe? Anybody find it yet? Like, is there an edge? Is there a wall that contains us? Like, the universe is limitless, right? From the outside, you know, God's looking down at us right now, and he's like, dudes, you're in the palm of my hand. Like, how hard is this? Why can't you find the edge? But inside, there's no edge. There's no wall. And the great thing about this is, if if you can't find the universe that you're in, you also can't screw with other universes, right? So, services and containers have to track their own resource usage. This is easy on the allocation side because we're generating the code, right? So anytime we have to call new, we just say, and in fact, I can show an, I'm running out of time, so I won't show the example. So we can just call new, and before we do it, we say, hey, do I have budget for this? And a budget is just a number either that counts down to 0 or counts up to something, right? And when we run out of budget, go to a safe point and figure out if there's budget up the chain, because everything's hierarchical. Now, as we allocate these, every object knows where it comes from, because first of all, there's a lot of rules about who can do what with what, right? We have no security rules within a container whatsoever. And the reason is because within a container, you only have your own data. And you can only touch the data in your own service. And the operations that the XVM can do, none of them do anything bad. You can add and you can go to, and that's about it, right? It's the simplest 8086 machine. There is no disk, there's no network, there's no clock, there's no console, there's no log, there's nothing. All those things, just like in a universe, like if you need something magical to happen in this universe, you better get down on your knees and pray, right? And it's the same thing. If you're in a container running code and you need something to happen that's not supported, you have to have it injected into your container. So all capabilities, and this is called a capabilities model in software, all capabilities come from outside the container. And so you don't know if you're at the top, if you're the container 0 at the top of the container hierarchy, or if you're 50 levels down running inside JUnit, doing some tests, or whatever. You don't know if you're in production versus not, etc. So you have no visibility to the outside world, and that's the basis for security, because having no visibility, no ability to impact the outside world, everything in your little universe is game to play with. So we tag all the objects with the container they're running in, but nobody tells us what the GC collects. And so this is the fundamental challenge that we have a solution planned for, but it's going to involve some C. All right, and with that, actually I was planning to stop at 40 because at 45 they kick us out. So we have 4 minutes for questions. I was planning for 5, and that's as close as I've ever gotten. So, questions? How ready is this is the question, and the answer is it's not ready. So the language is stable, the prototype implementation is stable. We're working on the production implementation. John?
So Erlang and actors come to mind, obviously.
Thank you. Yes.
And I think those don't have backtraces and scopes, but is that the main difference?
So Erlang, the question is about Erlang and actors. So Erlang has something called processes. That's what we call services. So if you ever used Erlang process equals ecstasy service. So I had never used Erlang, but after I shared this design with some friends of mine in the industry, they're like, oh, you copied Erlang. So so I had to learn a little bit about Erlang to figure out what I had missed, just in case. So Erlang is immutable, except it's not, and it is all message based across the process. So they use what's called a mailbox, so yes, it's very similar conceptually to Erlang. Erlang is it's subtly different, but very similar concepts in terms of why we made the decisions are very similar to why they made the decisions.
And I'll comment on the tagging of objects. That's going to come at a cost.
Yes, absolutely.
Density cost.
Yes.
And so does it kill your security if you allow approximate tagging? Like some objects can escape to a common pool, even if 90% of your objects are localized?
So with the original LLVM design, that's exactly what we're going to do. So just to explain it a little more clearly, what he's asking. So only when an object leaves a service does it matter what its tag is, and until then, it doesn't need one. So you can think of this as inflating a header in Java, the JVM, how it inflates a header of an object. And so when you have an object in one service, like in the example we gave where we were calling bar.bar or whatever it was, service.bar, that service is not the object. It's a proxy to the object. So anytime that you're talking to something, because anytime you call into that bar, it's not like when you're in the service that is the bar calling your own bar. There's an extra step you have to go through, and we represent that as a proxy.
Yes. There have been, I'll just say, there have been proposals for thread localized heaps in Java, which would come closer to what you need.
And that's what I'm referring to as arenas. Exactly. Arenas, I just stole the word from C++. So, all right, I think we are out of time. So thank you very much. I hope you enjoyed this, and have a great JavaOne.